is the outsourcing of private data and the delegation of some computation of this data, to some cloud services. And so you all know that this can be done in a secure way, in an appropriate way, if these private data are encrypted under a fully homomorphic scheme. Indeed, with such a scheme, what happens is that the result, the encrypted image of some data by a given Boolean function f, can be computed by homomorphically evaluating this function f at the encrypted data. But one of the major issues in these fully homomorphic schemes is that they have a huge ciphertext expansion. So typically, if we want to encrypt a single byte, then we need roughly 200 kilobytes of ciphertext. So this means that in practice, transmitting the data encrypted under the homomorphic scheme is something which is not possible. So instead, what we can do is that the user, so Alice here, can transmit her data, but encrypted not under the homomorphic scheme, but encrypted under a usual symmetric scheme, like here. And what she does is that she also transmits the session key, which is encrypted under the homomorphic scheme. Okay, so here, of course, in the key transmission, we have some expansion, but this is not a big issue because this has been done only once within the session. And so this works, obviously, if the cloud server is able to recover the data encrypted under the homomorphic scheme from what he receives. That means from the symmetric ciphertext and from the encrypted key. And if you look into more details, you will see that the operation that this server has to perform is nothing else than the homomorphic evaluation of the decryption corresponding to this symmetric encryption cipher. So this means that for such application, what we need is to find a symmetric encryption scheme, which is such that the homomorphic evaluation of decryption can be done in an efficient way. So what does it mean in practice? So in practice, what happens is that the current homomorphic schemes, they manipulate some noisy ciphertext, and the problem is that the noise level grows along with the homomorphic computation. And what happens is that a homomorphic multiplication leads to a noise growth, a noise level, which is much higher than what we have for a homomorphic addition. So in other words, this means that the noise level we will get at the end of the computation is roughly determined by the multiplicative depth of the function that we are considering. Of course, also the number of multiplication affect this noise growth, but really the main parameter is the multiplicative depth of the operation. So this means that our primary goal here will be to find a symmetric encryption scheme such that the corresponding decryption has a low multiplicative depth. So there has been many works, several works at least in this direction. So first of all, the multiplicative depth of decryption has been investigated for several optimized implementation of AES. And of course, some natural candidates for this are the recently proposed lightweight block ciphers. But it appears, if you look into more details, that the performances we get with this lightweight block cipher are usually much worse than what we get with the AES. And the reason is that these lightweight ciphers, they have been designed in order to minimize the circuit area. So this means they have a quite simple round function, but the counterpart is that they have many rounds. And a large number of rounds is, of course, something which is very bad in our case, because this corresponds to a high multiplicative depth of the cipher. And so, at last Eurocrypt, Martin Albrecht and his co-author, they have observed that our usual design criteria that we have for lightweight block cipher, they are not appropriate in this setting. And instead, what they did is that they proposed the very first family of block ciphers which are dedicated to this homomorphic application. So this is a family of block ciphers which is named LowMC. But the problem is that we need a dedicated and appropriate block cipher, but this is not enough. Because what we need in this setting, this is not only a block cipher, but a whole encryption scheme. What I mean is that we do not have only to encrypt some messages having a fixed length, we need to be able to encrypt messages of an arbitrary length. So what matters is not only the multiplicative depth of the block cipher, but the depth of the block ciphers together with its mode of operation. And so this is why we have revisited the whole encryption scheme, and as I will show in a minute, this has led us to the conclusion that the most appropriate type of symmetric encryption scheme in this setting, this is the set of all IV-based additive stream ciphers. And then a very good candidate for this is the stream cipher Trivium, and we also present a 128-bit key variant of Trivium, which is named Crivium. And as you will see, both of these stream ciphers have quite good performance in our setting. So before looking at the best kind of symmetric encryption scheme in our setting, we first have to look a little bit at this decryption operation here, because it consists of several different phases which behaves differently in terms of application. So what I mean is that first, usually in such a scheme, we have some offline phase which corresponds to the key setup operation, and this does not involve any data. So this is really offline, and then in many ciphers, we also have another offline phase, which now involves the key and some public material which has been transmitted, but this can also be done offline because the server then does not need to wait for the ciphertext. So we have these two offline phases, and then the output of these offline phases can be used as an input of the online phase, which is correspond to the operations which needs to wait for the ciphertext to be done. And then we recover the ciphertext, the encrypted data, but under the homomorphic scheme. And of course, in many operations, what we want to do is to reduce the cost of this online phase. And so this is why the best type of symmetric encryption schemes in this respect are the additive stream ciphers, because in an additive stream ciphers, the key stream can be generated offline, and then this online phase, it consists of a single bitwise exclusive OR, which is almost for free in terms of noise growth in our setting. Okay, so more precisely, what happens is that the scheme looks like this. So we have this offline key stream generation here, and this is the online phase with a XOR. And so what is a bit different to the usual setting is that because we need to limit the multiplicative depth of the circuit, this means that we cannot generate as many keystream bits as we want. So we have to stop at some point after generating a number of keystream bits. And then this means that we need to resynchronize the keystream generator to limit the multiplicative depth of this. So here in this scheme, this just needs that from the given public initial value, then we generate all these kind of frame numbers, and from each frame number, we generate the different keystream frames, and we generate the number of keystream frames, the number we need. And so what happens is that the function here, which expands the IV into these frame numbers, this is something which does not involve any secret material, so exactly the same function can be computed on the server side, and the only function which needs to be homomorphically evaluated is this f function here. So what we can do, of course, a natural choice is to choose for this g a simple counter, and then we can choose for this f here a block cipher. And so what this is exactly the well-known counter mode. But the problem with the counter mode is that it is secure, but up to the birthday bound. So this has been explained very well, this birthday bound and this problem by Atul yesterday. And so the problem is that in our case, of course, we would like to use for f a block cipher, but a lightweight block cipher in order to limit the multiplicative depth. And the problem is that most lightweight block cipher, they operate on rather small blocks, like 64-bit or 32-bit blocks. And so this is why this limitation, this birthday bound, it limits the number of plain text of data encrypted under the same key. And so in this setting, this provides really a strong limitation that we would like to avoid. So this is why we think that a dedicated additive stream cipher is much more appropriate in this setting. So a dedicated key stream generator, well, it looks like this. At each time instant, it generates from the initial state one key stream bit by extracting this bit from the initial state by some Boolean function f. And then the internal state is updated by the transition function denoted by this phi. And so we want this key stream generation to have a low multiplicative depth, and then this multiplicative depth, it's mainly determined by the multiplicative depth of the transition function, because this transition function is iterated many, many times, while this extraction function, it's applied only once for each key stream bit. So this means that in our setting, well, the constraints are a bit different from what we have in the usual setting where we want to minimize the number of gates used for implementing the stream cipher, because in the usual setting, then we need to choose both a transition function and a filtering function, which have a low cost, while here, only the transition function matters. And also, in the usual setting, we usually want to minimize the size of internal states, because storing this internal state, it costs some gates, while here this is not important. So this is a setting which is a bit different, and so this means that really our main constraints is to minimize the multiplicative depth of this transition function. So once all these constraints have been identified, then it appears in a quite natural way that a very good candidate for this stream cipher is a stream cipher trivium. So trivium has been proposed now 8 years ago by Christophe de Canière and Bart Prunier, and it was an eStream candidate, a candidate to the International eStream project, and it has been selected after this 5-year international competition, and it now belongs to the eStream portfolio of recommended stream ciphers. And so it's a very good candidate because it has a transition function which has degree 2 only. So the main parameters for trivium is that it accommodates a key size and IV size both of 80 bits. And the way it is initialized, it's quite classical for a key stream generator, is that we first put a key and IV into the initial state, and then we run the ciphers, the generator, several times, basically 1152 times, with blank runs. So that means that we run this cipher this number of times without outputting any key stream bits. So this is a picture of trivium. So as you can see, the internal state, it consists of 3 different registers. So the first one here is initialized with the key, the second one with the IV, and the last one with a constant. And so you can see that at each clock, what happens is that the content of every register is shifted to the right, and then we compute a feedback bit as a function of degree 2 of the bits in the register. And what is very nice is that this function of degree 2, it contains a single AND operation here. So we compute, for instance, here, the feedback bit from the content of the first register, and this feedback bit, it goes to the second register. Similarly, the feedback bit computed from the second register goes to the third one, and the feedback bit computed from the last register goes to the first one here. And so at each clock, so this is how the internal state is updated, and then the key stream bit is given by XORing some bits from the 3 registers here. And so what is important in our settings, so the main question is how many keystream bits can we generate like this if we want to have a circuit with a given multiplicative depth. And so this can be computed with a quite simple formula that's quite easy. And of course, this takes into account the many blank rounds that we have for initialization. And so what we get is that if we have a circuit with multiplicative depth 12, then we can generate with trivium 57 keystream bits. And if the depth increase, of course, this increase. So and now if we have multiplicative depth 13, then we can generate 136 bits. So this is quite nice, but the only problem we have is that Trivium can only accommodate 80-bit keys, and the reason of this is that this was the key size which was required in the eStream project. And the problem is that, so we would like to get a similar stream cipher with similar performances, but with a larger security level. And the problem is that there's no straightforward way to extend the key size in Trivium because there exists some algebraic attack, one which is due to Maximov and Biryukov in particular, which has time complexity 2 to the 84. So this means it's okay for the original Trivium, but we have no security margin to increase the security level. So our idea was that in our setting, because it does not cost in terms of performance, then we could construct a 128-bit variant of Trivium by increasing the size of the internal state. So this is nice because this does not a cost in terms of performance, but it offers better resistance with respect to some attacks like time memory data trade-off or algebraic attacks. So what we do in practice is that we add to the internal state two 128-bit registers, one corresponding to the key and the other one corresponding to the IV. So it now looks like this. So what you have in the middle here, this is the original Trivium, but we have two additional registers, one corresponding to the IV and the bottom one corresponding to the key. So these two registers, as you can see here, are mere shift registers. So we just shift the register and the feedback bit just come here. And so, but what happens is that the key bit coming from this shift register here is XOR to the feedback bit, which enters the first register. And similarly, the IV bit outputted by this register is XOR to the feedback bit going into the second register of Trivium. And also, the only minor modification we made compared to Trivium is that we changed the constant which is used for initialization, for the initialization of this third register here. So now, we can see that if we want to evaluate the number of keystream bits which can be computed with a circuit having a certain multiplicative depth, then we have roughly the same result as with Trivium. We only have 11 bits less than what we have in Trivium, and this comes basically from the fact that in Trivium, in this register, the last bits were constant, while here we have some key bits because the key is longer. So we have also, of course, analyzed the security of these variants, this variant of Trivium, which is named Trivium, maybe I didn't tell it. So, and so we analyze its security with respect to the main families of attacks. So as you can see, because we have a larger initial internal state, then we increased the resistance to some attacks like some attacks exploiting internal state collision. And also, something which is quite interesting, I didn't show it, but here you can see that the key bit coming from the key register here, it is XORed to the bit which produces the keystream bit. So this means that when you write down the equations corresponding to the value of the keystream bit, then we get one more unknown, which is one of the key bits coming from these key registers. So this means in practice that the time complexity of algebraic attacks increases because of that. Also, because we have these additional XORs with the key and the IV, then we get a better resistance to cube testers and all these kind of attacks. And we have a higher resistance to conditional differential cryptanalysis because we change the constant in the initial state, because those conditional differential attacks, they exploit the fact that many bits in the initial state of Trivium can be set to zeros. So what we did here is that we set many bits in this constant to 1 to avoid this kind of things. So let me now end up with some simulation results. So we have two series of experimental results which measures the cost of the homomorphic decryption corresponding to our ciphers. So these two series correspond to two different homomorphic schemes. So the first one is a BGV scheme, which is implemented with this HLib library. And something which is quite important when we perform this kind of simulation is the choice of the parameters of the homomorphic scheme. And what people do in most papers is that they choose these parameters in order to be able to accommodate the multiplicative depth that is required for decryption. But this is not very relevant, because if our server, if our homomorphic scheme cannot accommodate a higher multiplicative depth, this means that we won't be able to make some further computation on the data after decryption. So what we did instead is that we choose the parameters of the homomorphic scheme in order to be able to accommodate the multiplicative depth which is needed for decryption +7, and this +7 means that we will be able to perform some homomorphic operations on the decrypted data. And so these parameters corresponds to the results in red here. And so you can see then that in this setting, well, with Trivium, we are able to decrypt roughly 500 bits per minute. With a 128-bit variant, this drops to 300 bits per minute. And with low MC, this was higher. This was around 700 bits per minute. And, but I have to say that this version of low MC, it has a few security issues, because there's some interpolation attack on low MC with these parameters, which has time complexity 2 to the 118. So this means that we need probably to increase the security margin of this low MC, and we need probably to add a few runs, 4 rounds, was suggested by the designer, I guess. And so in this case, this means that this throughput must be divided by a factor 2 or 3. So now this is for the second type of homomorphic scheme, which is the Van Verkotteren scheme. And now it's a bit different, the performance, because we don't use batching in this case, so that's why the throughput are a bit worse. So what we have, if we run this on one core of our 48-core server, is that we are able to decrypt between 2 and 4 bits every minute. And then if we parallelize this, and if we use all the 48 cores, then we can increase the throughput to 100 bits for Trivium, something like 80 bits for the 128-bit variant, and 50 bits for low MC. So, but I would say that the main lesson that we can learn from this work is that the very nice performance which have been obtained by low MC, which is a dedicated cipher which has been designed for this particular type of homomorphic context, then we can reach roughly the same kind of performance with a firmly established cipher, which is Trivium. So, then I would like to mention 2 interesting open questions that remain. The first one is, so we have seen that with Trivium or with our variants, then we can have a cipher, we can construct a cipher which has multiplicative depth 12. And so the question is, can we do better? And how better can we do? And so in other words, what is the minimum multiplicative depth that we can have if we want to achieve a certain given security level? And in the full version of the paper, which is on ePrint, we present a completely different type of cipher, which is based on discrete logarithm, which is something which is really impractical because it's really slow, but it's interesting because it achieves a multiplicative depth, which is roughly the logarithm of the security level. And also, the last open question I would like to mention is that it would be nice if we could have some provable security result on this hybrid encryption scheme that we are using. So this is quite a standard hybrid encryption scheme, so we have many results on the security of this. The problem is that what we are using for encrypted the key is a homomorphic scheme. And then it does not satisfy the very basic security notion, like any notion like CCA security. So this means that we cannot apply the usual security results we have, and it's completely open, as far as I know, to get some provable security for this hybrid encryption scheme, and to find some reasonable security hypothesis for the homomorphic scheme to get results on that. So thank you for your attention.